let's start looking at this then. So the ring that we drew was basically a free body diagram, right? So for this box, we could represent the box as a dot for a free body diagram. And there's three forces acting on the box. You have this force, which is called what? Anybody? Gravity. And we find it by doing mg. So that's 3.2, the mass, times 9.8. So we got 31.4 newtons going downward. And then we have two forces up here. The first one goes this way, 55 degrees. So 55 degrees, and that's force one, we'll call it, is 17.7 newtons. And then this way, we have a larger force. And this is 160, so that, or 120, so that makes this 60. And force two is 20.4 newtons. So that's your free body diagram. Now the question is asking us, what are the x components and what are the y components of the net force, right? So we know from the last couple of days that we want to break every vector into its components. So how many triangles am I going to end up drawing here? Two, right? This one's right along the y-axis, so it's not going to require a triangle. But this one has an x component and a y component, as does this one. X and y. Now, if I solve for the x component of this triangle, I'm going to do 17.7 cosine 55, get 10.2. So we know there's the equivalent of 10.2 newtons pulling this thing to the right. And if we solve this one using cosine, we get 10.2 to the left, so I'll put a negative on there. So what is the total x component of the net force? 0, right? So there's no net force in the x direction. It's like both people are pulling equally in the x, so there won't be any acceleration either way because the forces are balanced. Now let's get the y's. So if we do 17.7 sine 55, we get 14.5. And if we do 20.4 sine 60, we get 17.7. So how much force is going up? 17.7 plus 14.5, which is 32.2 newtons. So that's how much is going up. But then there's also force going down. So we got to subtract that. 31.4 newtons down. So 0.8 newtons is the y component of the net force. Yeah?
65 degrees.
Isn't it 120?
Yeah.
So then 60 is 180, right? Total 180.
Oh.
It's all right. So 0.8 newtons is our y component. 0 is our x component. Does that make sense?
Yeah.
So if I were to draw this net force on here, it would be 0.8 newtons up. That is the net force. And we found that by doing component method. We didn't draw them tip to tail. We just made the triangles. If I asked you what is the acceleration of the crate, what would you tell me? Or how would you find it?
You do 0.8 divided by the mass.
Right. You would use Newton's second law. So now you know 0.8 newtons is the net force equals 3.2 times A. And you would solve for A. So really I could just ask, what is the acceleration? That'd be the only question based off of that diagram, and you could find it. You'd have to know to first get your components and get the net force. Now let's look at, just real quick, let's draw these tip to tail, just for the sake of what we did the last couple days. So the first vector is this one, 31.4. And now let's take the next one, tip to tail, and go 55, which is 17.7. And then vector 3 would be tip to tail there. It's 20.4 at 60 degrees. and then you draw your resultant in, right here. So what is the value of that? 0.8, right? That's what we found by doing that. We didn't draw them tip to tail, we just did components. We would find triangles again, it's the same ones we got there, and we get 0.8. So I think this is a little easier, maybe, now that you see
Yeah.
that. But we kind of had to lay the foundation the last couple days. So that's more in line with how we're going to be using these components.